Science is touching the life of humans. So if someone is sick, needs medicine. So if you need to develop drugs for a certain disease, you need to do lots of studies. If you want to have buildings, you need to study cement, steel, and so on. If you want to have clothes, you want to study textiles. If you're interested in history, you have to study the mummies, pigments, paintings, and so on. So I consider that each person in any society should be touched by the science that we are doing. And since synchrotron facilities are universal centers, that you can have so many beam lines, so many techniques, and so many applications. So what we do here is sort of covering all the needs of any societies.
Sinhrotron SESAME, svojevrsno naučno sunce Bliskog istoka, osvijetlio je mnoga istraživanja od 2018. godine od kada je postao dostupan naučnicima. Sinhrotron je akcelerator u kome se elektroni kreću brzinom gotovo jednakom brzini svjetlosti po kružnoj putanji u magnetnom polju, proizvodeći najširi mogući spektar elektromagnetnih talasa od infracrvenih preko ultraljubičastih do mekih i tvrdih rendgenskih zraka. Svi ovi tipovi sinhrotronskog zračenja pogodni su za raznovrsne eksperimente u bezmalo svim naučnim oblastima. Zato sinhrotron centri, kojih ima oko 60 širom svijeta, privlače istraživače svih profila koji, zbog prirode eksperimenata koje rade, jedino na ovakvim mjestima mogu razriješiti svoje naučne pretpostavke. Sinhrotron je jedno od najmoćnijih i najnaprednijih sredstava moderne nauke, koje pokriva istraživanje u fizici, hemiji, medicini, biologiji, agronomiji, ekologiji, arheologiji, nauci o materijalima. Kada bih vam rekla da voda može da poteče iz suvog pustinjskog vazduha i da se do tog otkrića došlo uz pomoć akceleratora koji se u potpunosti napaja suncem, rekli biste da vam pričam bajke. Ovdje, u srcu Bliskog istoka, u Jordanu, u Međunarodnom istraživačkom centru bajkovitog naziva SESAME, zaista se dešavaju naučna čuda. Čudo je i to što ih zajedno kreiraju briljantni istraživači iz zemalja koje su bile u konfliktima, političkim trvenjima, ratnim sukobima. Istraživači iz Egipta, Turske, Izraela, Palestine, Pakistana, Kipra, Irana, Jordana, udruženim snagama ovdje pomjeraju granice nauke i dolaze do nevjerovatnih rezultata. Na različitim eksperimentalnim stanicama radi se sa različitim zracima, a kako je riječ uglavnom o primijenjenoj nauci, istraživači imaju priliku da zaista mijenjaju ljudske živote i preokreću društvene tokove. Tako su hemičari Kraljevskog naučnog društva, vodeće jordanske istraživačke ustanove, došli do otkrića koje bi moglo riješiti nestašicu vode, jedan od najvećih problema sa kojim se Jordan suočava.
If you live in Jordan, you understand that problem because on a weekly basis or an every other week basis, we have big water trucks that come around and deliver water to our houses. If those water trucks do not come, then we don't have water for our daily use. And so a project that we started to take on in our lab was to create a new porous nanomaterial called a metal organic framework, or a MOF, that's crystalline, and we basically design it on the atomic level so that it can selectively capture water vapor from the humidity in the air. And so when we synthesize that material in our lab, we get these beautiful crystals, and we come to SESAME, and we use the beamline that's right behind me, the materials science beamline, to shoot X-rays at it. And because it's crystalline, the X-rays diffract, and then we can actually solve the structure at the atomic level of that material. Now, why is that important? Well, number one, we want to create a material for a purpose. And if we don't know what the structure is, then we don't know if we can meet that purpose. And so this beamline allows us to understand the structure to see if we actually made what we wanted to make. And so with that material, we then, when we solved the structure here behind me, we then built a device around this material to actually produce water directly from the air. And so there's 3 different compartments. The first compartment is what we call the air intake compartment. So air is blown through just from the surrounding atmosphere into a bed that is filled with the material. So it's a box full of the material. The air goes through it and it passes through the other side. But this side has moisture, humidity. This side does not. And so the water is stuck in there. And then when it's stuck and it's full, then we turn on a hot air that releases the water, and it comes over to a condenser that then produces actual liquid water. We can produce up to 35 liters of water per day per device. And so the cost to manufacture the device is around $600 US dollars, and the cost per liter of water produced is 6.4 US cents. So it's very cheap. It's about 5 times cheaper than your bottled water that you can get in the market. And now we have a way to produce water for anyone in Jordan living anywhere at any time. And so that's a very, very exciting prospect for Jordanian society that has this water security problem.
Za ovo otkriće eksperiment urađen u centru SESAME bio je suštinski važan, jer je izuzetno precizno snimljena atomska struktura materijala proizvedenog u laboratoriji. Za to su bili potrebni tvrdi X zraci koji u visokoj rezoluciji mogu da snime čak 1 nanometar, odnosno milioniti dio milimetra materijala.
So what a synchrotron does is it really increases the intensity of the light. And the light that we're using is an X-ray, and they're hard X-rays. And so because that light is so intense, that diffraction process is a lot stronger. So we get higher resolution data where we can really map out where are the atoms in this sort of 3-dimensional structure. And so the water harvesting project in particular could not have been done without us using this beamline.
All kind of materials we have in our nature are composed from atoms. So if these atoms are crystalline, so they are ordered in a way it is repeated in space in a periodic way. So we use X-rays and we hit the sample and we get the signal, diffracted signal out of this sample in order to study the atomic structure. So in this case, we need to understand why atoms behave differently. If you take an example like carbon, it can be graphite and it can be at the same time diamond. So these 2 materials, chemically they are same material, but physically they are totally different. So what we need to know why they are different, we need to study why atoms are, or how atoms are arranged in space. So this information is important in material science to tune materials in some cases to improve this specific property of these materials.
So we synthesize this material, and it might not be, we don't know what it is until we come here. Then we solve the structure, and that structure might not fit our properties exactly like we hoped for. So then we go back to the lab, we modify our synthesis to try to get the structure that we want. We again check it on the materials science beamline. And if we get it, then we move forward to the application stage. So it's a collaboration. We're not just users, we're actual collaborators at SESAME with the beamline scientists that are here.
Saradnja nije stala na ovom otkriću. SESAME je otvorio svoja vrata za još jedan zanimljiv eksperiment.
We have a problem called climate change issue, and that's caused by greenhouse gases. One of these gases was carbon dioxide gas, and it produced from human activities like burning fossil fuel. And me as a chemist, I have to find a solution. And actually, I did hundreds of reactions to get a result. Then I have a crystal. Actually, I didn't know what this crystal. Then I have a good result from X-ray diffraction. I came here at 17th of December before 2 years and to know what's this crystal. And finally, I have a good result about the material have affinity to capture CO2 selectively in the presence of other gases. Actually, the next step will be scale up of this material and using in a factory, especially in a humidity region, because this material have a selectively capture CO2 in a humidity, and use it in exhausting anywhere, CO2 from cars, from factories, from anywhere.
Synchrotron light has many properties that benefit researchers in understanding how matter is composed and made and built up. And I would quote at least two of these, which are the very wide range, which makes synchrotron light a very flexible tool that can adapt to many different kinds of experiments. It is a very multiform probe of matter, ranging from infrared to soft X-rays and to hard X-rays. You can explore different aspects of matter in different kinds of experiments and measurements. And this is extremely beneficial. It not only allows us to do things which do things better with respect to a laboratory, but it also introduces new kinds of experiments which would not have been thinkable relying only on laboratory sources of light, of radiation. So this is one. The other one is it is extremely intense and collimated. And this is obviously an advantage because at that point, having such a very narrow beam, it is easier to pursue tasks like selecting a finer energy resolution or concentrate a high intensity in a tiny spot on the samples, and this opens possibilities which are really not available elsewhere.
Na eksperimentalnoj stanici infracrvenih zraka mogu se odrediti biohemijska svojstva bilo kog materijala, od cementa, ukoliko naučnik dolazi iz industrije i želi da istraži osobine različitih komponenti i mješavina cementa kako bi poboljšao njegov kvalitet, pa do patoloških tkiva u medicini na osnovu kojih se može utvrditi priroda neke bolesti i način njenog liječenja. Na ovoj stanici, pod vođstvom naučnice koja njome upravlja, urađena su istraživanja koja se odnose na kancer, na rijetka oboljenja bubrega, kao i na mogućnost usporavanja Alzheimerove bolesti.
We give, let's say, biological information on the disease, but we also tend to correlate this information with the doctors, because they know much better the cases, they know much better the disease. So in order to try to give a new drug that can cure a disease, you just give some useful insights on the biology, on the chemistry of how this disease is progressing, and if you can also give some information on how to stop it. So for example, everybody knows that Alzheimer has no cure so far, but everyone is trying to slow down the progression of the proteins responsible for Alzheimer. Those are called amyloid proteins. So one of the experiments that we performed here, it's already published also, is that we got some brain tissues from mice, just as model for the experiments. And we tried to treat these tissues with plant seed, specific plant. And we found that this plant managed to slow down the progression of these proteins in the sense that the concentration of these proteins was sort of lowered down in the new treated tissues compared to the diseased ones.
Infracrveni zraci veoma su korisni za istraživanje arheološke građe i kulturnog nasleđa, pa je Džihan po dolasku u Jordan učestvovala u brojnim projektima gdje se kombinuju znanja iz hemije, biofizike, istorije, arheologije.
The first step actually is the samples preparation that we should work on. And all samples, those are related to cultural heritage, archaeology or art, they are quite fragile. Sometimes they are always of little quantities. So the first step in order to get good results is to have good samples. So we start by giving the users good advices on how to proceed with the samples preparation, sample manipulation. Then we start to work on the samples in order to, let's say, to specify which protocol we are going to measure the samples with.
Ovdje su rađene istraživanja zuba ljudi koji su živjeli prije 2000 godina u poređenju sa zubima savremenog čovjeka. Površina snimljenog zuba preko različitih indikatora, kao što je recimo procenat kolagena, priča priču o vrsti ishrane ili načinu života ljudi u dalekoj prošlosti.
Following the experiments in order to work further to reach an outcome, we need to do some data analysis, which is sort of mathematical applications or mathematical treatments that we do for the experimental data. Then we try to combine our expertise. I'm a biophysicist, but he's an archaeologist. So we try to exchange our information on the given samples. So he's giving me his expertise as an archaeologist, and I give my expertise coming from the experimental data, and we try to tailor and interpret how the story of the samples was eventually translated into scientific outcome.
Nekada je naučni rezultat od suštinske važnosti za očuvanje i restauraciju arheološke iskopine ili umjetničkog dijela. U ovoj laboratoriji od propadanja je spašena jedna vrijedna baptistička ikona.
The painting is about the 12 feasts of Orthodox in this region. We have seen there is a damage in the inscription. We have seen most of the pigment are damaged. We have firstly done the type of or the nature of the pigment by FTIR. If you see the damaged part, we can make small quantity and to see which material localized at this region. We have done it by Fourier transformation infrared. Then we have done the conservation for this icon. It's a very important icon for the baptism museum in the baptism site in Jordan.
Kulturno nasleđe se iz drugog naučnog ugla može proučavati na drugim eksperimentalnim stanicama. I to je jedna od mnogih čarolija sinhrotrona. Tamo gdje zastaje moć jedne eksperimentalne stanice, pojavljuje se druga koja će problem osvijetliti iz svoje perspektive. Na prvoj liniji mekih X zraka, koja će uskoro biti otvorena u centru SESAME, radit će se istraživanja u hemiji, ekologiji, istoriji, arheologiji. Prednost ove linije, koja je još uvijek u fazi završnih podešavanja, jeste u tome što se mekim zracima mogu proučavati skoro svi elementi periodnog sistema.
Most of the materials around us made from carbon, oxygen or nitrogen. And for cultural heritage, for example, you have a paper and they write something or they make some pictures on it and they use ink but you don't know the source of the ink. It's, for example, you don't know where it's come from, and there are several places in the world in those times who can produce inks. So, for example, this chemical structure of the ink which is produced in India will be different than the chemical structure of the ink which is produced in Anatolia or in Europe. So, by looking at that ink chemical structure, you can say that, oh, it's coming from Anatolia or it's coming from India. So, you can make a decision about the trade options between India and the place where you find this paper or where you find this picture or the writings, text.
Na liniji za tomografiju, koja je još uvijek u fazi konstrukcije, bit će moguće pomoću rentgenskih zraka dobiti slike u 3 dimenzije, što se često koristi za konzerviranje arheoloških predmeta, jer visoka rezolucija slike razotkriva obrazac oštećenja, formu pukotina, a da se dragocjeni uzorak ničim ne ugrozi.
We have used archaeological samples of ancient Roman glass. Glass is degraded during the centuries as it is buried in the ground due to mechanical forces or corrosion. Researchers are interested now that they have these samples which are 2,500 years old. They are interested in stopping this degradation mechanism, protecting the glass and understanding how this degradation happened. To do so, you need to look inside the glass and you don't want to break it because it's a unique sample. So you look at it with synchrotron light in 3D and you can reconstruct the pattern, shape or network of cracks. Looking at the shape of the cracks, you can study what caused this crack, how it evolved. And then you can combine it with other techniques like diffraction or IR, which are next door, and you can understand the chemistry of this degradation. So the synchrotron is a portfolio of techniques, and tomography generally is necessary to orient the analysis and really understand the history of a sample before you go on with other techniques.
Sinkrotron SESAME ima kapacitet za 25 eksperimentalnih stanica koje mogu da rade istovremeno. Svaka stanica je dizajnirana da izdvoji svjetlost koja po svojim odlikama odgovara određenoj tehnici i tipu istraživanja. Trenutno SESAME ima 5 eksperimentalnih stanica, 3 su aktivne, 2 će uskoro početi da rade.
When you come to work on a new beamline, you are appointed to construct the beamline, of course, with the help of other expertise, the technical expertise and scientific expertise as well. And then you are expected to operate the beamline, optimize the capabilities of the beamline in order to satisfy the demands of the users. We always say that the users have demands, and you have to satisfy the scientific community.
My role is to welcome users who want to run experiments with the synchrotron and with this beamline and guide them through all the processes involved in the experiment, from sample preparation, experiment design, and then also the experiment itself, how to position the sample during the experiment, collect the data, and finally analyze the data to get meaningful results, right?
Once the experiment is done, also we keep tracking the experiment and analysis for assisting users if they need any help, especially in our case. So we need to also get production, so scientific production in terms of articles and papers. So this is mainly our main role at the beamline scientist.
Iako su naučnici koji grade eksperimentalnu stanicu i rukovode njome, veći dio svog radnog vremena okrenuti naučnicima korisnicima i njihovim istraživanjima, postoji period u toku godine kada oni sami slijede svoju vlastitu ambiciju i rade svoje eksperimente.
They also have their own scientific life, so part of the beam time is dedicated to their measurements. And this is essential in any synchrotron, because you can only keep an instrument to the top level if you have the top people taking care of it. They must be motivated by their own science, their own curiosity, and their own work. So a certain amount of beam time is always reserved for the beamline scientists for their own research, which they can share in cooperation with other groups, and all this contributes to keeping up and maintaining a facility at the top possible level.
Na mjestu smo najblistavije svjetlosti koju današnja nauka i tehnologija mogu da proizvedu zahvaljujući sinkrotron akceleratoru. Elektroni u akceleratoru gotovo da dostižu brzinu svjetlosti i emituju svjetlost koja je i do nekoliko stotina triliona puta jača od klasičnih rentgenskih zraka. Pred ovom svjetlošću gotovo da nema naučnih tajni. Elektromagnetni talasi u sinhrotronu nastaju tako što se u manji akcelerator, takozvani booster, ubacuju grupe elektrona koji ovdje dobijaju ubrzanje. Nakon toga, elektroni ulaze u akceleratorski prsten u kome se kreću velikim brzinama. Kada elektroni, zahvaljujući magnetima u akceleratorskom prstenu, skrenu sa svoje putanje, oni emituju fotone, odnosno svjetlosni zrak koji je usmjeren u eksperimentalnu stanicu gdje onda ciljano dolazi na uzorak. Svjetlosni zrak izuzetnog intenziteta ovdje postaje moćno sredstvo u rukama naučnika.
In order to produce such light, we need to satisfy some criteria. For example, we need to satisfy such beam stability or the required beam stability. In this case, for the magnets, we should supply these magnets with a very stable electric current, and this task is done by the power supplies. And in order to give enough beam lifetime for the circulating electrons, we have to offer an environment for these electrons with very low pressure in order to reduce the scattering process with the gas molecules. And this task is done by the vacuum system. Now the electrons are circulating in a tube which is made of stainless steel and passes through all the magnets of the storage ring and keep rotating for many hours, as you can see from the screen. Another point is that now the heat deposited to the different parts of the machine, which is produced by either the electrical current in the magnets or by the power radiated by the electrons, this needs to be cooled down, and this task is done by the cooling system. In order to monitor and to know at each time the different parameters of the electron beam and the performance of the electron beam, we need to measure its size, its position, if there is some instability or etc., the value of the current, and these tasks are done by the diagnostic system.
Svi pomenuti timovi imaju samo jedan cilj, elektronski snop tokom dana i noći, jer neki eksperimenti su takvi da im je potreban kontinuitet od 24 sata, mora biti potpuno stabilan. I najmanje odstupanje u putanji ili brzini elektrona može dovesti do promjene u svjetlosnom zraku koji pada na eksperimentalni uzorak. Svi stručnjaci ovdje naporno rade da se ta situacija izbjegne, jer je kvalitet svjetlosti presudan za pouzdanost istraživanja.
Thanks to the long lifetime at SESAME for the electron beam, so we have almost 24 hours for the electron beam at 200 milliamperes and above. And this makes us doing injection once per day, which is enough for the users. So we agreed at SESAME that every day we make an injection or inject a new fresh beam in the storage ring at 8:15, for example, so that we dump the old beam, which already decayed to a lower current value, and then we fill the ring with the required current value, whether 200 milliampere, 250, or 300. So we can store now 300 milliampere. Depends on the user what they want.
Kada se svakog jutra okretanjem ovog ključa ubaci snop elektrona u akcelerator, ubrza i počne da emituje svjetlost, članovi operativnog tima u sobi za nadgledanje i kontrolu budno prate različite sisteme mašine za slučaj da se pojavi bilo kakav alarm ili se desi i najmanja promjena. Sitnije probleme rešavaju sami, no ukoliko je potrebno, odmah će kontaktirati eksperte iz pojedinih grupa koji dolaze da provjere sistem. Ako recimo primijete znakove rasipanja elektrona, pozvaće kolege iz tima za vakuum.
Vacuum is important because of the following. Now, electrons are circulating in the storage ring, and we need them to circulate for a long time. In this case, we have to reduce the gas molecules in their way in order to reduce the scattering or the deflection by these gas molecules. So we need to take out these gas molecules from the path of the electrons, and this is done by the vacuum system, simply.
Electrons are moving in the storage ring with certain energy, with certain speed, but to move the electron freely inside the storage ring, they must need a free space, a space free from all types of gases. They must be under vacuum. If we talk about the free space, it means the pressure must be too much below atmospheric pressure.
U sobi za kontrolu danonoćno se smjenjuju članovi tima za dijagnostiku, koji su, kako sami kažu, oči i uši sinhrotrona.
These are some of the eyes of it that we keep our eyes in the electron beam current. Here you can see, you can measure it. And also we can know in each current how it is the segmented currents with each train of punches here with this oscilloscope. Also, this beam is rotating and give a user a synchrotron light, and we take a part of it to ensure that this synchrotron light, it is very good by that one. That screen is giving us the beam size or the shape of the beam and its size, and that it is stable all the time. It is the same position, same shape, same size. Beside of that, you can see on the left of that there is some of the X and Y position, horizontal and vertical positions, and we do a more developed a way to know that even with many vibrations around SESAME or around the area, the beam is not affected with it, and keep the source point for the users stable as much as possible, with the accuracy plus minus can down to nanometers.
Elektronski snop je izuzetno osjetljiv na vibracije, pa se sinhrotron centri grade daleko od gradske sredine, jer vozovi metroa ili željeznički saobraćaj uznemiruju stabilnost snopa. Koliko je snop osjetljiv na bilo kakvo podrhtavanje, govori i činjenica da je u vrijeme nuklearne katastrofe u Japanu u Fukushimi 2011. u sinhrotronu Soleil u Francuskoj ovim mjernim instrumentima registrovana vibracija koja ometa snop elektrona. Zato je centar SESAME sagrađen na 30 km sjeverozapadno od glavnog grada Jordana, Amana. Ovdje se tokom godine smjenjuju naučnici korisnici iz regiona, ali i iz drugih krajeva svijeta, koji pismenim predlogom eksperimenta ubijede članove ekspertske komisije da zaslužuju da dobiju priliku da rade na nekoj od eksperimentalnih stanica. Broj prijava premašuje kapacitete centra, pa se pažljivo biraju kandidati koji će ovdje doći da sprovedu svoja istraživanja.
Synchrotron facilities are open to all scientists, and the way they can assess the facility is by submitting an idea of experiment that is called proposal, and this proposal for experiment is judged by an external panel, and according to the ranking, people can assess the facility obviously for free. So it's just a scientific merit that guide who will be the users of synchrotron facility. Each synchrotron facility in the world has a peer review committee that is doing this job. So ranking the proposal accordingly with the field of application and accordingly with the scientific content. So what I'm doing here is exactly this job. So providing support to the facility in order to select the best proposal with the most relevant outcome for the SESAME.
Ekspertsku komisiju čine stručnjaci koji dolaze iz sličnih centara, uglavnom iz Europe, koji vode računa da najbolji dobiju priliku da im SESAME otvori svoja vrata, da nijedan minut sinhrotronskog zračenja ne bude potrošen uzalud. Jer održivost je velika tema svih ovakvih postrojenja. Dijelom zbog toga što timovi stručnjaka danonoćno rade da bi naučnici imali što kvalitetniji svjetlosni zrak, dijelom zbog toga što je sinhrotron, kao svaki akcelerator, ogromni potrošač električne energije. Na 30 km od istraživačkog centra SESAME, specijalno za potrebe akceleratora, izgrađena je ova solarna elektrana, pa je SESAME tako postao prvi akceleratorski kompleks u svijetu koji se u potpunosti napaja obnovljivom energijom. Nakon što je 2018. centar SESAME samo na električnu energiju potrošio skoro polovinu svog godišnjeg budžeta, postalo je jasno da će se na spisku izazova brzo pojaviti pitanje ekonomske stabilnosti i održivosti centra. Pošto je sunce darežljiv energetski resurs u Jordanu, gdje u prosjeku ima 310 sunčanih dana godišnje, solarna elektrana je bila najbolje rješenje. Zato je vlada Jordana preko Ministarstva energetike preusmjerila $7 milijuna iz fondova Europske unije namijenjenih razvijanju čistih izvora energije na izgradnju solarne elektrane. Na 30 km udaljenosti od Alana, na strmoj padini neposredno ispod zgrade Jordanske komisije za atomsku energiju, postavljeni su monokristalni solarni paneli, zahvaljujući kojima SESAME već ima ogromne uštede i dobre šanse za ekonomski i ekološki održiv rad u budućnosti. Otkako je elektrana počela sa radom, računi za struju su drastično smanjeni, pa ušteda na mjesečnom nivou iznosi oko $300.000.
This power plant is 7 megawatt peak, so it produces on a yearly around 12 gigawatt hour energy, and this covers all the needs of SESAME. So yes, so it started working from March 2019, and it has produced more than 40 gigawatt hours of energy. And the performance actually is better than expected, and the power plant is actually producing about around 10 to 15% more than it was planned. And this all is achieved by a good maintenance and follow-up and everything on this plant. The system we are following here is called the wheeling connection. What does that mean? It means that we are actually in the point of connection, we are supplying the utility, but the main meter is actually recording a kind of credit. So they will credit us for the energy that we supply to them, but they will use it anywhere here in the region they will need. Exactly. But SESAME will use their own power based on their credit. So sometimes they will take from the plant directly, and some other times, no, they will take from the grid. So this is called the wheeling project, and we are following this scheme and this plant.
Monokristalni solarni paneli su veoma kvalitetni, ali su osjetljivi na nanose prljavštine, pa timovi zaposlenih, pored uobičajenog rada na održavanju sistema, svakodnevno čiste prašinu sa solarnog postrojenja, jer zbog konfiguracije terena i čestog vjetra, prašina pokriva uređaje i panele, što može oslabiti njihovu efikasnost.
We take all necessary requirements to keep the station is working well. Okay, and we check all station equipments via monitoring system and via visible check. It is important things that the cleaning of the PV modules, because the dust is reduce the productivity of the panels. So the cleaning is a very important thing to increase and ensure that PV modules is products its capacity as well.
I tako, u ovoj naučnoj bajci na Bliskom istoku, sunce u potpunosti pokreće akcelerator koji proizvodi svjetlost 10 milijardi puta intenzivniju od njegovih vlastitih zraka. Iako bi se po ovome reklo da je nauka nadmoćnija nad prirodom, ipak nije tako. Sinhrotronsko zračenje u kosmosu postoji odvajkada. Naučnicima na našoj planeti je postalo dostupno tek u prošlom vijeku, 1947. kada je prvi put uočeno u laboratoriji i to kao neočekivani efekat jednog istraživanja u New Yorku. Tek tada su se ljudi konačno približili ovoj blistavoj svjetlosti koju su vjekovima prije toga mogli da posmatraju samo u zvijezdama i galaksijama, ne znajući da je ona rezultat ubrzanja elementarnih čestica u ogromnim magnetnim poljima u vasioni. Zahvaljujući modernim teleskopima, puni spektar zračenja može se zapaziti na snimcima poput ovog, gdje se vidi Crab nebula, ostatak jedne zvijezde udaljene od naše planete 6000 svjetlosnih godina. Sinhrotronska svjetlost, stara koliko i same zvijezde, posljednjih decenija postaje jedan od najmoćnijih instrumenata savremene nauke. Prošle godine proslavljena je 75-godišnjica otkrića sinhrotronskog zračenja.
I would say also, as many others, they say that the synchrotron is a magician. So it's a facility that you cannot mistake. And if you need, as I said, to work on anything that touches the society in any field, if you come to a synchrotron as if you are going to a magic land, you find so many techniques, you find so many ways to solve specific problem or to find a new drug or to to solve a mystery about something in the history about our predecessors or so on. So the celebration came actually on time, and I think that if we were given the opportunity, I think we should celebrate every day.